Demonstration for our final project for BME 547 medical software design. We designed an ECG analysis tool that will allow anyone with or without programming experience to explore a ECG signal and apply different methodologies to it like a data scientist would. So here is our homepage of our application. As you can see, if you're not logged in, the upload data functionality would not be available to you. But if you do have an account, how we have it set up right now is you can directly log in. So we already made an account for you, Dr. Ward. As you can see, we uploaded some previous data sets to there. So if you already have an account, this is what will happen. If you refresh it, since the authentication state is not stored in a session or a cookie, it will just basically bring you back to this page, the home page. And then now let's think of a case where that you do have account. You don't have account. Then now the application would automatically create a account for you and add you to the Mongo database. So here, as you can see, this is a new account, so there's no data sets associated with it. So to start our analysis, we can work on this upload data button that now works. Currently, we accept .csv, .numpy, and .text files. We prepared a ECG data in NumPy format, and this is a sample data set that we have. So we can open this, and then with this, you can upload this to the Amazon S3 bucket, which is then linked to the MongoDB. And now with this data upload, you can see this is stored as your data set associated to this user. And now you can perform a certain analysis. To start off, I think a good point is to visualize the signal. So we can go to the Visualize Signal tool, select the specific data set, and then by default, if we have a n time that's really large of an arbitrary number, it will show the entire signal. And for this signal specifically, we have a sampling frequency of 1000 Hertz. So let's run this. And wow, we have the entire signal plotted. Say we want to only look at a middle section of this. We can do, say arbitrarily we want to see 20 seconds. We can do 200 to 220 seconds, and we run it. And boom, this is our segment from this time to this time. So let's say we want to proceed our analysis with only using this segment. So we want to take the segment out. We can use our segment signal tool. Again, select this specific data set from 200 to 220 seconds, again with a sampling frequency of 1000 Hertz. Run it. And then, wow, we have this new data set that's stored and accessible across your tools. That is the cut signal. Just to demonstrate a little bit, we do have some form validation here. If you have some nonsense here for the start time, it will say it's incorrect type. If you have bad values, or if your start time starts after your end time, something like this, it will say end time cannot be before start time. So we do have some form validation going on right there. So with this new segment, we can go back to our visualize signal and then look. So this should be 20 seconds. Of course, you can do arbitrary. So here it plots the entire segment. Say we only want to look at 2 beats, so maybe that's like about 2 seconds. We can see our ECG signal with the P wave, the QRS complex, the T wave are exhibited here in this plot. So let's go back to the full signal, the full segment. Here's some motion artifact that might be caused by the movement of the device when this signal is recorded. And typically before other feature extraction or whatnot, we want to remove this baseline render. We have the apply filter tool here that you can simply run. And then this will generate a filtered signal. Again, if we go back here, visualize this filtered signal. And then beautiful. We no longer have this baseline render. Amazing. So now with this filtered signal, we can move on to extracting some features from this. So selected this data set and then extract features. And boom. So these are some typical ECG features that we have. And then specifically here, the QT interval is smaller than usual. So it's labeled as abnormal, and we alert the user that this is an abnormal value. Just to show this is not static, we can run it for another one. And maybe this one. So see the abnormal value change since the HRV value now is outside of the normal range. Moving on, let's try to detect some peaks from this. So with this filter cut signal, we run this, and then boom, the peaks are detected here and displayed over the plot. In the future, we might even want to store this as a separate file or array that allows the user to perform whatever cool analysis they want to do with those peaks. So lastly, we want to show out this spectral subtraction functionality. From what we experimented, a threshold of 0.0019 and Windows has a 5 works well with this signal. So spectral subtraction removes large motion artifacts. So by running this, we'll have this subtracted signal. Since we don't really have a lot of abnormal data in this specific data set, you wouldn't really see a difference. But if we would have a really high peak, the spectral subtraction would remove that. So yeah, that sums up this tool. We can return to home and then refresh this so we see the previous data sets that we worked with are displayed for this user. Refresh to log out. Say, let's try logging in again. I think it was this account. And yeah, we still have those data sets and we can continue wherever we left off. Yeah, so that is our application. Thank you very much.